As we push the boundaries of quantum computing, we might be standing at the threshold of a reality more expansive than we ever imagined. Are we ready to explore it? In 2019, Google made headlines with a groundbreaking achievement in quantum computing. Their Sycamore chip performed a calculation in seconds that would take classical computers thousands of years, demonstrating quantum supremacy. But what if this leap in technology could do more than revolutionize computing? What if it could unlock one of the most thrilling concepts in modern physics, the multiverse? In this video, we'll dive into the fascinating connection between quantum computing and the multiverse, uncovering possibilities beyond our wildest imagination. Quantum computing is a revolution in computing rather than just the faster version of the traditional systems we are familiar with. It is possibly unlocking new areas of computational power that we can barely imagine yet. An excellent example of how quantum computing is breaking all boundaries is Google's incredible achievement with its Sycamore chip. The core of quantum computing lies in qubits, quantum bits. Unlike classical bits, which can be only 0 or 1, qubits exist in multiple states at once because of quantum effects such as superposition and entanglement. This means that quantum computers can process huge amounts of information in parallel, not one step at a time. In other words, quantum computers do not just work faster, they work in a completely new way, allowing them to solve problems that would be impossible for classical machines to solve. In 2019, Google stunned everyone in the tech world when the Sycamore chip delivered a major result: to solve a random circuit sampling problem in just 200 seconds. Not a slight achievement. Classical supercomputers were the global leaders back then. It would take about 10,000 years to accomplish this calculation. So why is this important? The task Sycamore tackled was designed to be nearly impossible for classical computers. The task consisted of generating random quantum circuits and sampling their outputs, a process that grows much harder with every additional qubit added. Classical computers that process information one step at a time are overwhelmed by these kinds of calculations. However, Sycamore can take advantage of quantum superposition in all 54 qubits to do this job much faster and more effectively than any classical machine could ever hope to do. This achievement marked the first true demonstration of quantum supremacy. The belief that quantum computers could accomplish certain tasks far better than classical systems at their best. Being only a proof of concept, its significance cannot be overstated. Sycamore's success has proven that quantum computers can solve problems that are otherwise practically impossible for even the most powerful supercomputers to solve. But that is where things get even more exciting. Google's quantum breakthrough opens up the door to deeper questions about the nature of the universe itself. Could these quantum systems, having solved complex problems, open up new possibilities in the multiverse theory? As quantum computers tap into many different states and parallel possibilities, some scientists are only just beginning to think that these such systems may represent a new means of probing for parallel universes. Suppose quantum computers can access so many states at once. Could they, in a sense, explore other realities in a manner that sheds light on the most profound mysteries of our cosmos? This is the kind of thinking that's driving the next stage of quantum research. With Google's Sycamore chip, it's not just faster computations, but a potential new era where quantum computing could change everything from AI to cosmology, even perhaps our understanding of reality itself. The Multiverse Connection. The multiverse theory is perhaps one of the most provocative and debated concepts in modern physics. It questions the very nature of our existence. The universe we see around us may not be the only one. Indeed, it might mean that there are infinite universes with different properties, laws of physics, and perhaps even completely different outcomes from the one we experience. These universes, or parallel worlds, may exist alongside but not accessible to us under any conceivable mode of conventional observation. The core element of this fascinating theory is the many worlds interpretation, or MWI, quantum mechanics, a radical paradigm for trying to understand quantum reality. The MWI was first put forth by physicist Hugh Everett in 1957. In this theory, every quantum event, whether it is a particle interacting with light or an electron changing energy levels, doesn't just choose one outcome. Instead, every possible outcome is realized in a different branch of the universe, creating a separate, parallel world for each possibility. Consider the behavior of a quantum particle like an electron. In the classical world, an electron would be in one definite state at the time it is measured, either here or there, in one state or another, but it's not so in the quantum world. According to the MWI, each time a quantum event occurred, like the state of the electron is measured, it produced a branching point where each possible state actually occurred at the same instant, but in different universes. So even if we only experience one of these states, the other possibilities are manifested in parallel realities. This means that each and every decision, every outcome, and every event could spawn an entirely new universe where an alternate version of reality plays out. MWI is the conceptual framework that makes sense of some of the baffling phenomena in quantum mechanics, including such things as superposition and entanglement. Superposition happens when particles exist in multiple states at once. As an example, think about an electron being here and there simultaneously. Classical physics would struggle to explain how this could happen, but MWI suggests that these multiple states are not just theoretical constructs, they are real and occur in different branches of reality. Similarly, quantum entanglement, the phenomenon where particles become linked across vast distances, influencing each other instantly, could be understood as particles that are connected across parallel worlds, rather than simply behaving strangely in our single universe. But here's where it gets even more mind-boggling. What if these quantum phenomena are not just abstract concepts, but could reveal insights into the fabric of the multiverse itself? Could the very tools we use to manipulate quantum particles, quantum computers, be key to exploring parallel realities? This is where the fascinating intersection between the many worlds interpretation and quantum computing begins to emerge. In fact, some theorists claim that with increasingly powerful quantum computers, such as Google's Sycamore chip, we may well be creating tools to access several parallel realities. Why? Because these computers rely on the same principles on which the multiverse theory was based. The principles governing qubits, existing in superposition and entanglement, might be sufficient for simulating and interacting even with tapping into those described parallel worlds in MWI. Indeed, the Sycamore experiment was a breakthrough that showed what quantum computers can do. The problems that would take a few thousand years to be computed classically could be easily solved by quantum computers, and so on. But if quantum computers can, across several possibilities of qubits, manipulate these states, then perhaps, just perhaps, they might be interacting with different branches of reality, as MWI theorizes. Some scientists even believe that the extreme complexity of quantum systems may even allow a quantum computer to create new parallel universes, or, at least, give us tools to study them in ways never before imagined. Take, for example, quantum tunneling, in which particles can pass through energy barriers that they could not cross according to classical physics. Quantum tunneling could represent a kind of window between universes, an event that links two parallel realities. If that were the case, would not quantum computers, able to explore many states at the same time, harness this phenomenon to gain insight into the multiverse? It's still in its infancy stage, but the potential is just incredible. Quantum computing could transform fields like cryptography, medicine or artificial intelligence, and unlock the secrets of physics to solve its greatest mysteries. Further developments in our understanding of how quantum systems work may one day allow us to not only create more powerful computers, but to explore the very nature of reality itself, tapping into the multiverse in ways that seem science fiction, but may be grounded in the science of tomorrow. How quantum computers might tap into multiple realities. The reason why quantum computers are far ahead of traditional computers in terms of their incredible capacity to process a vast number of possible outcomes at the same time is due to the very principles of quantum mechanics. Bits, which are used in classical computers, can exist in only one of two states, either a 0 or a 1. Quantum computers, however, use quantum bits, or qubits, which can exist in a state of superposition. A qubit can represent a 0 and a 1 at the same time. This enables quantum computers to see and compute thousands of possibilities simultaneously, meaning they are much more powerful for certain difficult calculations. When Google's Sycamore chip carries out its quantum calculations, it doesn't look just for one possible answer, one at a time, but rather examines many possibilities at once, due to superposition and entanglement. This introduces an interesting idea. Quantum computers might work in several different realities at the same time. Each reality could show a different result of the quantum process, and each outcome might link to a new parallel universe. Even though it sounds strange, this theory has some exciting potential for future discoveries in both physics and computing power. The Sycamore chip has 53 qubits. That is the giant step for quantum computation. But the power in quantum systems arises from how that number scales. As one increases the number of qubits, the computer's ability to process information grows much faster. This isn't merely a linear scaling. In fact, a quantum computer could, in theory, simulate and process information from almost infinite parallel universes if there are enough qubits. One can imagine each universe being a potential outcome guiding the quantum system toward the best solution much more efficiently than a classical computer could do. To understand this better, we need to look more closely at quantum entanglement. This happens when qubits get linked or entangled so that the state of one qubit directly affects the state of the other, no matter how far apart they are. Albert Einstein famously called this spooky action at a distance, and it is still one of the most confusing parts of quantum mechanics. When qubits are entangled, they can do calculations that classical systems cannot do. Quantum entanglement allows quantum computers to do many calculations at the same time by instantly connecting qubits in different states. In simpler terms, this means quantum computers might not just be finding a solution, they could be using the computing power of parallel universes. The idea is that when these quantum computers solve a problem, each possible outcome exists in a different universe. Quantum systems may be capable of accessing those universes at the same time. This means that quantum machines can do more than we can see and enter other realities. Although this idea remains unproven, the concept is being studied and developed in quantum mechanics and quantum computing. As quantum systems evolve, it may be that the relationship between quantum computing and the multiverse can be made more apparent. Quantum programs could be designed to better utilize superposition and entanglement to explore all the possibilities available to parallel universes. These could then lead to discoveries in solving hard problems, like simulating molecular interactions in order to find new medicines, streamline supply chains, or break encryption codes. One of the exciting aspects of quantum computing is its potential to redefine the limits of computation. With each advancement in quantum hardware, whether it's through Google's Sycamore, IBM's Eagle chip, or other quantum devices, the boundary between scientific ideas and computational reality becomes increasingly blurred. These quantum machines might assist us in better understanding quantum phenomena, but they may further reveal information about the nature of the multiverse. In short, they shall be able to expand upon our understanding of computing as well as reality. As quantum computing becomes better, it may give us useful tools to look into these theories. Just as superposition lets qubits look at many states at the same time, quantum computers could help us examine many different realities, giving us a clearer understanding of the multiverse. Therefore, even though we cannot yet see or directly engage with these parallel worlds, quantum computing could help us understand them better. Does achieving quantum supremacy hint at the existence of parallel universes? Google's Sycamore chip has been declared to have achieved quantum supremacy. This technical milestone also carries important implications beyond computer science. This raises an interesting question: whether quantum supremacy demonstrates that parallel universes exist. Until recently, this was thought to be pure science fiction, but now it is being taken more seriously in the field of quantum mechanics and its possible connection to the multiverse. Quantum supremacy occurs when a quantum computer can do some job that ordinary computers are incapable of doing, no matter how strong the world's supercomputers might be. Google's Sycamore chip showed this by solving a very difficult problem in just a few minutes, something that the best ordinary computers would need thousands of years to complete. But the question remains: what's really going on in quantum systems that enable them to do things that no classical machines can? One of the most interesting ideas is that quantum computers like Sycamore are actually accessing something much more powerful than the classical laws of physics. This is similar to the many worlds interpretation, MWI, of quantum mechanics. The idea here is that every quantum decision, whether it be the spin of a particle or the outcome of some quantum measurement, new possibilities are created. In essence, all possible outcomes of a quantum event happen in another parallel universe. Could it be that quantum computers are, in fact, using multiple realities at the same time in their computations? Maybe they use parallel universes to help solve impossible problems. It is here where things get very interesting when considering the connection between quantum supremacy and the multiverse. According to MWI, quantum systems do not choose one result when the measurement is performed. They create many results in different worlds, and each shows a different result of the same event. Suppose quantum systems, like Sycamore, can handle many outcomes in parallel. In that case, it means such systems might be using an enormous network of parallel universes to look at all possible solutions at once. Imagine this: for every calculation Sycamore does, it is not working with data within our universe. Rather, it's interacting with many overlapping realities, where every reality shows a different path and a different possible solution to the problem. This could increase the power of quantum systems by letting them look at nearly endless numbers of possibilities very quickly, many more than conventional computers can do. This concept of quantum systems using parallel universes has exciting implications for what reality is and how computation works. If such quantum computers can really connect to a multiverse of different realities, that would mean computing is not a simple process happening in one universe. It may be a process that takes place in many connected realities. This would also change how we think about the limits of what can be done with computers, since the physical rules of our universe would not limit quantum computers. These ideas, even though speculative, have strong support in the actual nature of quantum systems. Quantum mechanics was long known for its strange and counterintuitive properties, such as superposition and entanglement, showing that quantum systems may simultaneously exist in multiple states or influence each other over huge distances. If quantum supremacy is proven to exist, then there might be a possibility of changing our understanding of the universe. From this point of view, reality is not static and unchangeable, but rather an extremely large network of possible worlds that are connected with one another. The consequences are huge. It could imply that quantum computers, like Sycamore, are more than just using power through quantum physics. They might unlock the potential to explore a multiverse of realities once thought of as fantastical. If quantum systems are indeed interacting with parallel universes, then the very nature of computation, and perhaps even reality, might be far more complex and interconnected than we have ever imagined. As we learn more about quantum computing, the exciting idea of parallel universes could help us make great strides, not only in technology, but also in philosophy, physics, and what existence really means. How quantum chips like Sycamore can model complex systems such as black holes, dark matter, and the early universe. Besides being able to solve some problems faster than their classical counterparts, quantum computers can do much more. Indeed, one of the most interesting applications of quantum computers is to simulate complex systems that go beyond the limits of regular computers, such as black holes, dark matter, and how the universe began. At the center of this possibility is the power of quantum physics. Quantum computers can handle many different possibilities at the same time, allowing them to study the complicated connections in systems that are very difficult to simulate with regular computers. These systems include areas of physics where many things interact in very complex ways, like how matter behaves under extreme conditions. Consider, for instance, black holes. These massive objects are formed when a star collapses in on itself. They have gravitational forces so strong that nothing, not even matter or light, can escape from them. Complex quantum processes control black holes, but it is very difficult to understand how these processes work at a basic level. Regular computers cannot handle the huge amounts of data and complex calculations required to model such a system. Quantum computers might be able to simulate extreme conditions that can't be created with regular computers. Using quantum connections and being in multiple states at once, quantum systems might allow for the representation of behavior around a black hole. At this mysterious boundary, gravity is so strong that time seems to slow down. It is said that quantum computing will enable us to learn about dark matter. Dark matter refers to the invisible stuff that makes up about 27% of the universe's mass, but can't be seen directly. Dark matter affects regular matter through gravity, but it doesn't give off, take in, or reflect light, which makes it very hard to find using normal methods. Some quantum algorithms could be applied to simulations of large-scale behavior of dark matter. This will help researchers come up with ideas that, in the long run, may help in detection. Additionally, just after the Big Bang, the early universe was a very hot, dense, and chaotic place. Modeling the behavior of the universe during this time requires understanding how fundamental particles and forces interact in a way still impossible with regular computers. Quantum computers, however, can simulate the theory that explains how particles interact and behave at levels that current technology cannot achieve. Quantum systems might be used to investigate strange and extreme places in order to uncover some of the biggest secrets of the universe. If quantum computing is related to the multiverse, then maybe the simulations would not only teach us about our universe, but also give us knowledge about other possible universes existing in the multiverse. Potential breakthroughs in fields like medicine, cryptography, and AI. Quantum computing has effects not only in theoretical physics and astronomy. In reality, the actual applications of quantum technology have slowly begun appearing in areas like medicine, encryption, and artificial intelligence, or AI. Medicine will greatly gain from the power of quantum computing. Quantum computers could be game changers in simulating molecules and chemical reactions. Traditional computers cannot simulate large molecules, for instance, when studying complex interactions such as protein folding, which is key to understanding diseases like Alzheimer's or cancer. Quantum computers would model these processes at the quantum level. This could revolutionize drug discovery and new medical treatments. On the other hand, quantum computers might both pose risks and offer new opportunities in encryption, because they can break virtually all the encryption methods to date for protecting sensitive data. For instance, based on Shor's 1990s quantum algorithms, breaking down extremely large numbers is much easier than on a classical computing platform. This makes basic encryption techniques like RSA encryption vulnerable. But it also introduces new opportunities for quantum-resistant encryption methods that may protect data in the quantum age. Quantum computing could be the next revolution in AI. Machine learning algorithms, which are data-heavy and require a lot of computing power, may work better with quantum processors. A quantum computer might process huge amounts of data much faster than an ordinary computer, which could help AI systems learn better, make better predictions, and solve more difficult problems. In addition, quantum AI may bring major advancements in language understanding, problem-solving, and decision-making capabilities. For example, it may help AI systems understand and predict how humans behave, making things such as self-driving cars and personalized suggestions more effective. These advancements could greatly help those fields, but also pose serious ethical and social issues. The power of quantum computing may make certain tasks or calculations faster. However, it introduces new risks. Better development of drugs and more personal medicines can be helpful for society. However, they will further worsen problems of access and fairness if not managed wisely. Quantum technology has so much to offer, and is only recently starting to reveal what it can do. But of course, this great power comes with great responsibility. We need to think carefully about the effects of such technologies as we continue the journey of exploring and further developing them. Potential consequences of interacting with parallel realities. Should we even attempt to do so? It is very exciting and confusing at the same time to imagine using quantum computers to get in touch with other realities. However, such technology brings very big, important questions concerning ethics and practicality. If quantum computers, for example, Google Sycamore, can indeed reach different universes in order to solve tough problems, what could happen because of that? And more importantly, should we try to do it? The major issue here is the ethical dilemma of tampering with parallel realities. If quantum systems can interact with parallel universes, then we have to ask ourselves whether we have a right to interfere with or alter what occurs in those other worlds. If each parallel universe represents a different version of reality, some of which could contain sentient beings or alternate versions of ourselves, intervening in these worlds could have an unpredictable, unknown consequence. Could we, for instance, unknowingly disrupt the course of life in another universe? If such alterations were to take place, could the actions be irreversible? These are the questions that venture far beyond the realms of traditional technology ethics. The results of interacting with parallel realities could be very serious and even dangerous. For instance, what if what happens in a quantum system in one universe upsets the basic structure of another? Could changing one reality cause a chain reaction, a series of events leading to surprises in other realities? This, in and of itself, has significant potential to touch and reach out to a vast array of universes simultaneously. The changes may cause ripples that can alter the very physical laws of not one universe, but many of those within the entire multiverse. Scientists and ethicists must be cautious when it comes to the threat of such machines, in connection with the danger of adjusting the very basis of the structure of reality. But that's not all. Ethical concerns do not stop there. What if these quantum systems, which were supposed to help us solve problems in our universe, accidentally started changing the basic laws of nature in our reality? Could quantum computing, taken to its limits, start changing the fundamental constants of nature, like the speed of light or gravitational forces in our universe? Technology is new, and we have serious concerns about some unforeseen effects on our world. The fine-tuning of space-time and the laws of physics governing our universe might be weaker and less stable than what we consider, and this could lead to unknown threats by mixing and bringing in external quantum forces. The closer the researchers look at quantum entanglement and superposition, the more real it becomes that quantum computers could connect to parallel worlds. But then, if we start to look into these many realities, we should not forget the possible problems and dangers involved. What if being able to access these worlds causes a major crisis for our existence? As we try to create new technology, can we forget the importance of ethics? It might bring results we may not anticipate or control. Furthermore, we are concerned that we might not be prepared to bear the tremendous weight such powerful systems entail. We already see glimpses of how AI, machine learning, and self-operating systems can create problems we least expect. Quantum computing might even make things worse, as it would grant us access to many universes. Progress should be balanced with care and caution as we continue to develop these technologies. These big questions about the responsibility that comes with having such power, the possible effects of changing alternate realities, and the dangers of changing our own need careful thought. As quantum computing goes further than before, we must think about not just the practical benefits it could offer in areas like medicine, cryptography, and material science, but also the possible ethical problems that could arise. After all, the more control we have over reality, the more we need to ask ourselves, should we really try to control it? As we move closer to full utilization of quantum technologies, we must be cautious. We should ask not only what we can do, but also what we ought to do. And perhaps the most daunting question of all is, what if we lose control of these strong systems? What if we lose control of quantum technologies? It is both exciting and scary at the same time. So the question is, what happens if we lose control of these systems when quantum computing starts to become part of the real world? It's not a technical issue, but a philosophical one. Progress versus responsibility. On the technical side, quantum systems are fragile. Qubits are the fundamental units of quantum computers and are highly susceptible to external influences. Even small variations in temperature, electromagnetic interference, or even cosmic radiations may cause a quantum state to collapse and, hence, lead to errors or system failure. Quantum decoherence, the loss of stability in quantum states, is one of the greatest challenges faced by scientists. In simple terms, it is hard to keep a stable quantum state long enough to do useful calculations. As quantum computers grow larger, with thousands or even millions of qubits, this weakness becomes a big problem. The more complicated the system, the greater the chance of a serious failure, which could cause major issues or incorrect results. If we cannot control these systems reliably, the risks become much higher. But the technical problems are just the beginning. The actual danger could arise from how quantum technologies are used. Quantum computers can break through the security codes that protect the global communication and money system, thus presenting a very strong tool to cybercriminals or hostile states. Imagine a world where data supporting global security, banking, and communications is prone to hacking by quantum. Bringing quantum systems into artificial intelligence could create big problems. AI, when used with quantum computing, might behave in ways that people cannot foresee or manage. Independent systems could develop and make choices that are beyond human comprehension, resulting in cases where we no longer fully understand the effects of what we have built. There is a scary chance that quantum technologies could reach forces or knowledge that people are not ready to deal with. Quantum mechanics is a mystery. What happens in the very tiny particle world is not easy to understand and often goes against common sense. If, in fact, quantum systems do depend on multiple universes or change the structure of space-time, then it can be very dangerous to approach them, because we would find much stronger forces than ever. The idea that one day we might open passages to unknown places or alter the fundamental laws of nature is terrifying to consider. Could running a quantum program make our reality unstable, and maybe even other realities too? As quantum computing progresses, the rules and safety concerns start becoming very relevant. It needs clear standards so these technologies do not fall into the wrong hands or get misused. Governments, researchers, and the international community need to coordinate in their pursuit of the safe and ethical advancement of quantum computing. Otherwise, we may end up with a dark quantum future by rushing into this sphere without considering the possibility of some unintended effects beforehand. In the final analysis, the question of whether people should pursue these quantum technologies and how far we should go with their capabilities is more than a matter of science. It raises serious moral questions about power, control, and responsibility. The more we advance in the quantum world, the more we have to be careful.